tell you about my work and about these concepts. I really would like this to be an open table, if possible. So, hello. So feel free to stop anytime if you have questions, if you have comments, if you want to add something, and let's make this like more as interactive as possible. I understand we have about an hour, so I will leave maybe some time at the end for some questions, but you know, you're welcome to ask along the way. The other thing I need to ask you is, everybody understands me? Do you all understand English pretty much?
Yes.
Yes, okay. I apologize, my Bulgarian is not really good, and in fact it's not. I would like to be able to speak the language, but yeah, it's really, you know, hard for me. So, this is the best. Unless you want me to do it in Italian, I can do it in Italian too, but I don't think so. Alright, so let me start. Let me give you a little bit, you know, let's put this in perspective. My background is this. I come from physics. I am formerly a researcher in physics. I got a PhD from the University of Stony Brook in the United States, and I also graduated from Cornell University. I've always loved theater at the same time, and you know, I've always been torn between the two things. I like art, I like theater, I like science, and I didn't know what to do with my life. But they kept giving me scholarships for doing physics and never gave me any scholarship for doing theater. So, you know, at one point you just follow the bigger river. But then at one point you decide that maybe you should make a decision yourself and not accept the fact that other things make decisions for you. So I decided that I should try to make a living out of theater. But at the same time, I never lost my passion for science. And so I tried to combine these two things in this project called Jetpropulsion Theatre. And you're welcome to go check out this website, not now, later. And but at the same time, I still work at the University of Trento in Italy as a teacher, and I teach a course on science communication. So the two things, you know, work together for me. And today's topic will be this: beauty in science. Maybe along the way we can talk more about it. Why I want to talk about this, but you know, maybe now the most important thing for me is that the idea of today is to convey a sense of wonder and a sense of curiosity around science. And you know, beauty will come afterwards. I think the most important thing is to understand that nature for us is a really beautiful thing. And we just have to learn how to look at it with the eyes of somebody who is curious. And that's the whole point today. So, let me start from our big boss, Albert Einstein. He said something very interesting. He said a lot of interesting things, and we will come back to him later. But he did say nature is subtle, but it's not malicious. Nature never wants to hurt, never wants to do it, you know, doesn't have a conscience. And therefore, we are looking at something which is waiting to be discovered. And that's the whole point. But I want also to read this quote from Isaac Newton, who is the other boss of all the physicists. And because his way of looking at things is very similar to what I believe we should all have. And I will read this with you. And he said, "I do not know what may appear to the world, but to myself I seem to have been only like a boy playing on the seashore and diverting myself in and now and then, finding a smooth pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me," which is really the essence of every researcher. And let me say an extra thing: it's the essence of every artist. Artists and scientists share exactly this vision. This is what I think, of course, and you're welcome to disagree. If you don't agree, just say I don't agree and we can talk about this. But to me, it's true. We are looking at little things and getting very excited about little things, and in front of us there is this amazing beauty. And sometimes we actually lift our eyes and we look at this beauty, but then we come back to the little pebbles. But that's because we're humans and our brains, can only go so far. But we are moving in the direction of discovering things. And that's what Newton, Einstein, and other amazing giants have been doing. So today we talk about beauty. But let me just say this. I don't know anything about beauty in the sense that we are going to talk about it, but it's one of those concepts so big that what can you really say? You can say everything and you can say nothing. So that's why I keep telling you it should be like an exchange of ideas. But for sure we can say this, that if we look at nature, nature has two characteristics which somehow are linked with the idea of beauty. Surely nature has a special love for symmetry. Harmony, the balance of proportions. Anything you look at seems to have symmetry. Like the brain, we talk about the brain. The brain has a left and right hemisphere. Our bodies, anything in, hello, hi, welcome. So that's for sure one thing that nature is continuously telling us, that symmetry is a key. And then economy, the desired effect of using as little as possible. I mean, nature always wants to save energy. And I don't mean energy in the physics sense, but to make things as economical as possible. And that's another part of what I consider beauty. So we look at this, and I believe that very often, in many different ways, and that doesn't have to be literal, in art we are doing exactly the same thing. So, let's now dive into the idea of discovering this beautiful world. How should we approach the concept of science? And let me just give you an example. I believe that by example we can understand better. When you look at a little child, the little child, a baby is sitting at the table with the mother trying to feed the baby. And so the mother will go up to the baby and maybe give the spoon with a little, food to the baby, and the baby goes and throws the spoon away. But throws the spoon away because the baby wants to see the food flying in the air, wants to discover how long it takes for the food and the consequences of seeing the mother cleaning the floor. But not because the baby is mean or terrible, just because it's the way to discover the world. And if you have babies, you know that very often babies will just throw things around. So you give, more food to the baby because the mother feels compelled. The baby should eat. Because if the baby doesn't eat, the mother is very worried that the baby will be sick. But the baby knows that the mother wants the baby to eat. So the baby loves to throw more food around because the food will keep on coming. And it will keep on coming in all kinds of foods. And so it's a beautiful game between the baby, the mother, and the world, gravity, whatever. And I think that this is the right approach. It's called the playing position. In theater we call it the playing position, but it is the same approach that I have seen studying the lives and the biographies of great geniuses, like we mentioned before, Albert Einstein. So, the first thing to approach beauty is to develop our sense of curiosity and our sense of wonder. How do you do that? Well, again, there isn't a recipe for these things, but there is a way of using your mind to think about things. So let me tell you about Proxima b. Proxima b is a planet that has been recently discovered by NASA that lives, is a planet that lives in the golden region of Proxima Centauri. I don't know in English, I think it's pronounced Centauri, yes? Alpha Centauri, Beta Centauri, and Proxima Centauri are the three stars closest to the Earth, only about 4 light years away from here. It's very close, light years. 4 light years is very close compared to the size of the universe. And they discovered there is a planet there that looks a lot like the Earth. And so, you know, they had this artist rendition of what this planet could look like. It doesn't mean it looks like this. But, so, when I say sense of curiosity and a sense of wonder, all we have to do is look up into the sky and look at this amazing thing that is up there, and we can let ourselves be carried away by the potential and possibilities of discovering things. And so this is the closest planet to us that looks like the Earth, and it's not in our solar system. And look, there are 3 stars. You see, one is Proxima Centauri, and then Alpha Centauri and Beta Centauri. So this planet actually has some really curious orbit because it belongs to a 3-body system. And if you know anything about physics, you know that 3-body systems are very complicated to solve. And so it has a very strange orbit, and but it's beautiful. And so scientists will you know, look at the news, terrible things, the wars and all the ugly things, and move them away sometimes, and then look at these results and say, this is what the universe is like. It's much more exciting. So the question that we continuously should have is, what wonders do we still have to discover? And let me tell you this, you don't have to be a top scientist to discover wonders. And now I want to give you an example. I give you an example from Richard Feynman. Have you ever heard of Richard Feynman? Yes, you have. You too have. Yes. But maybe other people haven't. Richard Feynman was an amazing scientist. He was a great physicist. He won the Nobel Prize in Physics in 1965. But mostly he was an amazing thinker. He always was curious, and he said things like this. He said, if I cannot destroy something and build it back again with my own hands, I have learned nothing about it. So whenever at school they would teach him things, he always had to take things apart, understand them, and put them back together. And that's how he became one of the greatest physicists of all times. And he had a lot of anecdotes in his life. And so let me give you this anecdote, which I believe is very fascinating. And this is to prove to you that you do not have to be a great scientist to discover things. So Richard Feynman used to say something like this. You know, he said, I have a friend who is an artist. And sometimes he takes a position which I don't agree with very well. He will hold up a flower and say, look how beautiful it is. And Feynman would say, yes, I agree. But then the artist would say, I, as an artist, can see how beautiful it is, but you, as a scientist, take it all apart, and it becomes a dull thing. This is what the artist would say. And Feynman would say, to me this is really stupid. First of all, because the beauty that the artist can see is available to all of us. We can all see the beauty of a flower. We can appreciate the beauty of a flower. But we can say much more about the flower if we know some science. We can imagine the cells inside it, the interactions which do have a beauty. I mean, there isn't just a beauty at the dimension of a centimeter. There is a beauty also at a smaller dimension, the interactions. But also the fact that the colors of the beauty, the colors of the flower developed. Yeah, beauty now is becoming part of my brain. The colors of the flower developed in order for it to attract insects to pollinate it. It means that insects can see colors. And so this raises some interesting questions. Does the aesthetic sense exist also in lower forms? Like in bees, for instance? I mean, could it be that humans and bees share a very similar sense of beauty? So maybe I'm looking at a flower, next to me there is a bee looking at the same flower, and both of us are thinking, wow, this is wonderful! Yes? You see, there is a connection between humans and bees. And it's not some sort of supernatural connection, some common god or something like this, you know? It's a real connection. Both of us are looking at the flower, and we're thinking, amazing. And this is just thinking about flowers. You don't have to be a scientist or a researcher to appreciate this. You know, it's this way of thinking that leads people to make great discoveries and leads people to appreciate the beauty of things. Again, I'm not giving a definition of beauty. I will not give it to you today. I'm not an expert in this. But I can tell you how scientists approach the beauty of the universe. So, stop me. Do you understand everything I say? More or less? If you don't, stop me. You know, I'm sure somebody will translate something, and although they said translating is complicated, but look at this. It's an example of beauty. It's a perfect circle. Again, you know, economy and symmetry. By looking at this, you could look at this for a long time and get wrapped up and start to wonder about the universe. You can see the sun in there, you can see the moon, you can see the earth, you can see a lot of things. And you can see this. This is pi. It's one of the most exciting numbers. You know, it has a lot of deep secrets in it. It's very much connected to the circle I just showed you before, or to the sphere, and who knows, maybe to the same shape of our universe. If we believe that the universe is spherical, I don't know if we can. Maybe you are a mathematician, maybe you can help me understand this, but maybe we believe it. But this number is very much linked to a lot of things that have to do with the way we perceive the world. And yet, it's a very simple number. Look, you can generate it just by a very simple formula. Of course, you need to go to infinity with this formula. Don't try this at home. It takes a long time, but you can. And it has, it has a long sequence of numbers. And as far as scientists know, these numbers don't repeat themselves. You don't get to a point where they start again. Nobody has ever been able to find that. But this number. And again, I'm telling you all of this because I want to show you that you can find beauty in things even if you're not a scientist or even if you're not a researcher. Anybody learns about pi and the connection of pi to our universe, to the circle, and you start to look into the numbers of pi, and there are some people that devoted their whole life studying this thing. But you know what? If you look hard enough, inside that, you can find your date of birth. If you really look hard enough, and you have, a gazillion years to spend, somewhere in there, you will find exactly the sequence with your date of birth. But you know what? You also find the sequence with the date of your death. There is everything in there. That number has everything, only that it needs to be discovered. Once again, it's like Newton looking at the pebbles on the beach and then all of a sudden lifting the eyes and seeing something bigger than that. Of course, it's not a big secret that you can find the date of birth because, another thing, you can put a monkey in front of a computer, a typewriter, and the monkey starts to type. And if you wait long enough, the monkey will type the whole Hamlet. But you have to wait a long time. But who knows, what maybe time is infinite. Although we can talk about this later. So the question is, what hides in its folds? What mystery is hiding in pi's folds? Now, let's talk about truth. Because a lot of times, beauty, truth, they all seem to, if something is beautiful, it has to be true. But who said that? Why should it be? And sometimes scientists make the big mistake. No, I don't mean scientists, I mean people who think about science make the big mistake to think that whenever a scientist says something, it is true because it's proven. But in fact, scientists know very well that it's possible to unprove something, but really it is not possible to prove something forever. Maybe in mathematics is a little bit different, but in physics, for sure, you can never say for sure something is like this, because even that might eventually be disproven in a few years. Okay? So what is truth? And I don't know, I just put a big question mark. But I can tell you something about the way truth and beauty work together. Look at this. These are the 5 Platonic solids. And there are only 5 of them. And these solids are the only solids that can be built with the use of polygons, regular polygons that, at every angle they meet in the same way, at every corner they meet in the same way. You cannot build other solids besides these ones. In fact, they have been known since antiquity, since several thousands years ago, as being very, very special. And Plato wrote about it, and Aristotle wrote about it, and they have been, let me show them again. They said because these are so special, there aren't any other ones. They must be linked to our universe, to our life, to the elements. And that kind of thinking is non-scientific. It's not something a scientist now would do. But certainly in the metaphysics era of Plato and Aristotle, it was possible to think in these terms. And so look, fire was linked to the tetrahedron because it's very spiky, this one, right? Then water to the icosahedron, where is it? That, because it's smooth. And so Plato said, of course, water is made of these elements. Earth is made of this element. Because Earth is, you can pack cubes very solidly. These kinds of thinking. And that is air, because it's a little bit like fire, and it's a little bit like earth. And then he was left over with this, with the dodecahedron. And he said, well, you know what? This is the shape of the universe. So you see, what I'm trying to tell you is that truth and beauty don't always work together, but it's great to think about them. And I can imagine Plato getting really excited when he was thinking about these things. And in fact, for something like 2,000 years, it does actually lasted like an idea. So, okay. But the question we have now is, what does it say about the structure of our universe? Why are there only 5 Platonic solids? I don't have an answer to that, but it certainly is a question that a lot of people are asking. What does it say about our universe? So, let me continue along this trip. As I said, I'm not telling you about beauty, but I'm telling you about how exciting it is to think about nature and to think about our universe in terms that are very simple questions that anybody can ask. And let me add another thing. This is a very good way, an interesting way to talk about science to students in classes. They hardly ever do that. I know it because I interact a lot with teachers, professors, scientists. They hardly ever mention curiosity, wonder, and beauty whenever they talk about science. They only give you formulas, and this kills the soul of the students. But on the other hand, in a very simple way, you can raise the souls of the students. Let me give you an example now that I find it so simple and yet so exciting. Look at this. This now maybe some of you hate science, maybe some of you don't like physics, but just accept the fact that I tell you some physics now, and it's very simple, okay? This is the gravitational force. Very simple. If you believe that gravity is a force, if you study relativity, gravity is not a force anymore, but let's not worry about that. So, G is a constant, M1 is the mass of the Earth, say, M2 is the mass of the Sun, and R is their distance. So, it's divided by R squared. This force is what allows us to do this, jump around. It's what keeps the Earth and the Sun together in the solar system, what keeps, the whole solar system, but not only that, it's what keeps the different solar systems in our galaxy, the Milky Way. They are connected by this force. It's quite an interesting force. Proxima Centauri and our Sun talk to each other all the time thanks to this. But not only that, all the galaxies in our universe exist because of this force. So this force is fundamental for the existence of our universe. And this is the electrical attraction and repulsion force. Q is a constant. Q1 is the charge of the electron, say Q2 is the charge of the nucleus, divided by their distance squared. This force is what keeps together the electron and the nucleus together. It's also the force that holds together the atoms in the molecules, and the molecules in the objects, like this one. See, that's why it's so solid. And that's why if I jump, I don't go through the floor, and I stop here, because this force is so strong, you know? It's another very fundamental force for the existence of our universe. Now, do you notice any similarities?
Yeah.
No, they are very different, right? One is Q, one is G, I agree. No, the point is that they are the same mathematical form.
The law.
Say what?
The law.
The law, yes. But it's a big mystery, you know. It's something that is not easily explainable. Here we're talking about charges, and here we're talking about masses. They are very different in nature, and yet, look, it seems that there is some sort of rule that goes beyond the mass and beyond the charge, and it's telling us something. Only that you look at it for a long time and you don't understand what it is, and in fact it's not very easy, and scientists are working on it. But what I'm showing you is that these two things somehow belong to the same family. But why? In school they never show you this really. Only that this one is so much stronger than this one. This one is 4.17 times 10 to the 42 times bigger than this. This is big. This is 1 and then 42 zeros stronger than this. But we never see this. I mean, it seems to us that we never see it. And that's another mystery, because it seems that the electrical positive charges and the negative charges in our universe are equivalent, so they cancel out each other. And so our universe is neutral. You see how many things we can ask ourselves and say, why is it neutral? And we can spend the whole day walking around like, why is it neutral? I don't know, give me a coffee. And it's crazy. And yet, this is what science is telling us, but very simple science. You can open any book, from high school. This guy, Ernest Rutherford, he was the first one to talk about this, and he it's a very funny story because he was a physicist from New Zealand. He won the Nobel Prize in chemistry in 1908. So it's a long time ago, more than a century ago. But he was a big, very important physicist, and he would go, to all the conferences and talk about physics. And he was so proud of himself, and he would say things like, in science there exists only physics. Everything else is stamp collection. Of course, they gave him the Nobel Prize for chemistry. He was really angry about that. But anyway, so he was the first one to suggest that the nucleus, the atom works just like a solar system, with a little the electrons running around. There is something that doesn't work quite like that. The way that came here, this guy Niels Bohr, and you see our friend Einstein. These are two giants. Niels Bohr said, yeah, well, really, it's not true. The electrons don't move around like planets. They've got some strange shapes, but mostly, they are quantized orbits. To each orbit corresponds an energy. But the most important thing is that the shapes of these orbits doesn't look at all like the ones of the planets. And that's another thing that we should understand in discovering science. It's that we should never base our judgment on our experience with everyday objects. We always have to do with objects that behave in very simple ways, like this coin here. It's made of a lot of atoms and it moves very slowly. But then, when you actually use particles that move really fast, like if you look at the protons and antiprotons at the CERN collider, in Geneva, they move at the speed, almost at the speed of light, and things, very crazy and peculiar things happen. Because nature is simple, but it hides its things. So, this brings me to the next interesting topic. in coming up with this idea of beauty. And it's this, intelligence. We have the ability to think about our world in a sense, and that's another one of the most amazing things that, it's still nobody has ever really understood is we are stardust because we come from other, explosions of stars somewhere else before the beginning of our solar system that somehow managed to get a conscience. It's an amazing thing. Again, one of those things that sometimes I start to think about this and I don't know how to get out of this stuff. This thing doesn't have a conscience. It doesn't know it exists. It cannot look at itself and discover things. But we have it, but we are only made of atoms, just like anything else. And that's another crazy thing. And you cannot tell me this is not linked with beauty somehow, right? So, coming back to Einstein, because when we talk about intelligence, Einstein was a master and relativity. I mean, look at an amazing feat of intelligence he did. He managed to understand that the speed of light is invariant, is independent on the reference frame you're in. It always goes at the same speed. And therefore, if you believe that, space and time become entangled. They become one part of this four-dimensional world. And when Einstein came up with this, and it happened in 1905 and then again in 1915, first with special relativity and then with the general theory of relativity in 1915, people say, yeah, it's great, but how would you be able to prove it? Well, it has been shown to be true, and that's the most amazing thing. And what has been shown to be true is that time stretches depending on the speed that you're moving. And so let me show you another beautiful experiment, which I believe, again, should excite our minds and should make us be really happy to be alive on Earth, to be able to see these things. Let me tell you about the experiment of cosmic rays and muons. Now, cosmic rays is another one of those mysteries. There are these very highly charged particles coming from the cosmos, hitting the Earth all the time. And usually they are protons, very highly charged protons. Who knows where they come from? As if there is somebody outside, shooting protons at us. We don't know where they come from. But they hit the upper atmosphere, and then they do this cascade thing, giving birth to all kinds of other particles that are very short-lived. And they live very, very little, short times. And some of them are muons. Now, muons are these very special little particles, very somewhat similar to electrons, only they're much heavier. And they're created in the upper atmosphere, and they live extremely short life. They should be able to travel only for maybe 200 or 500 meters before they decay. So we should not be able to see them. Well, it turns out that we are continuously hit by muons coming from the upper atmosphere. I mean, we really are. If you could see them, you'd be like, oh my God, muons, stay away from me, even inside. Because muons, because of relativistic reasons, their time for us stretches to several milliseconds, if I remember correctly. That's enough for them to come down to the Earth and hit us. Now, that's an amazing effect of Einstein's relativity. And it was all produced by the ability of not just one man, because Einstein developed his theory together with a lot of other people, really, but the ability of human brains to think about the world and ask questions and discover things which somehow seem to be hidden from us. And so, this beautiful example of these muons being able to come down all the way to us because their time is stretched, and so their life becomes really long compared to what it should be, is a great effect of relativity, and it was understood by a genius like Einstein. And therefore, to me, it's another example of beauty. Another example of beauty is this, incommensurability. It's a strange word. It's big, something big. And now we're coming, to more like the philosophical side of things. Look, when you look at this, when you lift your eyes and you open up your eyes to the universe, all of a sudden you realize that the universe that we can observe has something like 100 billion galaxies. Now, 100 billion is a big number. If you really made a calculation, now you might ask, how do we know this? But don't worry, I'll tell you maybe later, but just trust me, it's a fact. I don't know if it's true, but it's a fact right now, we believe it. 100 billion galaxies, and in each galaxy, on average, there are 100 billion stars. And then there are planets running around each star. So if you calculate all of the planets that should exist in the universe that we can observe, there is something like 10 to the 23 planets. Now, 10 to the 23 is a big number, is bigger than the number of all the grains of sand on Earth. And which it's almost 100 times bigger than the number of all the grains of sand. Which means that there are so many planets in this universe, and who knows what incredible wonders are going on there. Maybe, and I am sure there are some planets where there is a conference just like this one, or somebody going around telling people about the universe, and looking at us, and maybe we are connecting with this people, and when we talk about beauty, we should be able to really get excited about this stuff. And when I talk about education, I think this is exactly what we should teach students, children. Okay, so coming back to this picture. This picture is it's a very famous picture taken by NASA, by the Hubble Space Telescope over the span of about 10 years. And what's amazing about this picture is that what you see here are not stars. These are galaxies. And if you look hard enough, you can see galaxies that look just like the Milky Way. So somebody in there is, cooking eggs and potatoes right now. And it's an amazing thing. In this little square, there are thousands of galaxies. And let me show you how small this square is. If this is the size of the moon, this is the square we were looking at. Let me show you again. This is the square, and this is the square. You see that?
Wow.
Isn't that amazing? So now you take this and you multiply for the whole size of the sky, and you come up with 100 billion of these things. That's how they came up. Now, with the number of the grains of sand on Earth is more complicated, but nevertheless. All right. So look at what we're looking at. A very, very small part of the sky. That's the amazing thing. Let me show you this little video. It should show you how much we are zooming into the extreme deep field that we were talking about. It's zooming and zooming and zooming, and we are getting. Yeah, there it is. Yeah, there it is. This is it. All right. So, again, I'm not sure I know. Now, I don't know why I put this. It's just to show you 100. How big is 10 to the 23? Just gives you an idea. But so what? While this thing is going, let me just take this. This is why I think that we should really get in touch with science and teach science to people, because it shows us what is our place on Earth. It gives us a way to look at our existence, which is very different from the way that we look at in our average daily life. I think that so much beauty in science is exactly this. It's the fact that we get very excited for the very small lifespan that we have on Earth, because we only live, whatever, 80 years, 100 years, hopefully, maybe less, compared to the size of the universe in time, and during that little window, which is even smaller than the window I showed you before, we have the moral duty to continuously try to understand things. So whenever they tell me why art and why science, it's this. Art and science are the only two things, the only two disciplines, as far as I understand, and this is what I believe, that are looking forward, are looking to understand new things, are creating new things. And we have this duty, I think. Okay, let me come to, other issues which I believe are quite important, and stop me if I'm going too long, okay? 4 minutes?
No, 40 minutes up to now.
Ah, okay, yeah, so I still have a little bit of time. Yes. If you get bored, say something and I will stop, okay? But the most exciting things are coming. So you cannot be bored. The brain is another amazing thing. We were looking at this amazing thing up there, now we're looking at this amazing thing down here. The brain is built of these things called neurons. And you remember, I told you that there are something like 100 billion galaxies. Well, guess what? There are about 100 billion neurons inside a human brain. So there is an incredible connection between the brain and the universe. If anything, because the brain has got the same number of neurons as we see galaxies. And each neuron is attached to other neurons through these synapses. And there are thousands and thousands of synapses that are attaching each neuron to other neurons. So the brain is another incredibly complicated machine. And once again, the beauty of it is that it's made of atoms, just like a chair, just like this mirror, and yet it has a conscience. Where does this conscience come from is a big mystery. Some people advocate, God or something like that. I like to believe, in more concrete ways that there is some way our biology works. But nevertheless, it's an amazing thing, and that's another issue that I want to raise your attention to. Now I don't know why this video goes forever, but it's quite interesting. It shows the connections between different neurons, and it's more like an emotional video. Of course, you shouldn't believe it too much. It's not like somebody went inside with a microscope looking at things, but still. Okay, so for me, the universe and the brain are extremely similar. In the universe, you have the different galaxies talking to each other through the gravitation force, and inside the brain we have these electrochemical reactions and the currents moving electrons from one neuron to the next. Let me move forward. Let me tell you about the extension of the brain, where we are going now with our brains. And let me tell you about artificial intelligence. I put a question mark there because really some scientists are saying you cannot have artificial intelligence. In my opinion, you should be able to remove this because it's only a matter of it depends on how you define intelligence. But computers have been able to do things which up to a few years ago were deemed impossible. Well, chess, but we're talking about 1990s, 1997, I believe. Deep Blue managed to beat Kasparov, if I remember correctly. So chess has been already game mastered by computers a long time ago. But just recently, the game of Go, the Korean game of Go, was mastered by a supercomputer, IBM. Google, and then poker. Now, of all of these, poker is the most difficult one because you can bluff. And so you would think that a human should always be able to beat a computer, but not. Now, artificial intelligence scientists have developed ways to have computers beat humans at poker. But let me tell you an example of how amazing this is. For the game of Go, I think the name was Lee Sedol, was the name of the grandmaster that managed to, match this Google computer to see who could win and go. Everybody thought that Lee Sedol would win without any hesitation. Well, Lee Sedol managed to lose the first match, the second match, and the third match. And Lee Sedol was very, very worried because it was like humanity was losing to a machine. So Lee Sedol decided in the fourth match to not play by the rules anymore. He made some crazy moves. The computer got lost. And Lee Sedol won the fourth match. But artificial intelligence now has got this thing called, the machines can learn from their own experience, deep learning and things like this. And in the fifth match, the machine had already understood all the possible crazy moves that Lee Sedol could move and anticipated them and won the fifth match. And essentially now nobody has been able to win and nobody can win. Now imagine the same thing carried on to other extents, in our life. And it's quite interesting and somewhat also quite worrisome. I was at a conference by Bill Phillips. He won the Nobel Prize in Physics some years ago in Bose-Einstein condensation and other issues like that. Anyway, Bill Phillips now is very much into artificial intelligence, and he told us something which to me is amazing. That now computers are discovering laws of physics that scientists don't quite understand. They've gotten to the point of such a deep knowledge of science that scientists are not able to grasp the results. To me, it's amazing. It's scary, but it's a great opportunity. It's a great opportunity because we come back to the idea of beauty. Because one, I think it's beautiful that humans have been able to create machines that raise the level of intelligence. Second, what is the reason that we live? We live in this universe, in my opinion, because we have to try to understand its mechanisms. There is no other reason. I mean, we can reproduce and have a great time, but then we die. But maybe our moral duty is to continuously learn new things. Now we manage to find the help of these machines to help us learn new things. And I think it's a welcome thing. Of course, it has to be regulated. Stephen Hawking, Elon Musk, and other thinkers have been saying that before we move on with artificial intelligence, we should stop any research on artificial intelligence, write down the rules of engagement with artificial intelligence machines, and then continue to develop artificial intelligence, because we could get to the point that artificial intelligent machines will take over our lives. And that's a real risk. And it will not be too far away in the future. But nevertheless, let me show you this video now that tell us something about amazing machines and what they do. You know how hard it is to walk in that terrain and not fall over? And this machine is able to do it. On the snow. It's not hitting any trees. looking at the jobs of the future. You know, these things are going to take over a lot of jobs. And off it goes into the future. So I showed you this not because I want you to get scared, because it is strange. And these machines were not programmed to react. They can take any abuse. In a sense, it's like Asimov, if you know Asimov. You know, the 3 laws of robotics. Yes, but nevertheless. I think this is an incredible future we're looking at. All we need to do is to use our brains to make it happen in a nice way. All right, so I'm coming to a conclusion. As far as I understand, we should stop. I will not read this big mama to you because it's too long. But remember Richard Feynman. Yeah, let's read it. It's beautiful. Let's listen to me. I stand at the seashore alone and start to think. And there are rushing waves, mountains of molecules, each stupidly minding its own business, trillions apart, yet forming white surf in unison. This is what I've been telling you about all day, all during this hour. Ages on ages before any eyes could see, year after year, thunderously pounding the shore as now. For whom, for what? On a dead planet with no life to entertain, never at rest, tortured by energy, wasted prodigiously by the sun, poured into space. And might makes the sea roar. This is Richard Feynman. Deep in the sea, all molecules repeat the patterns of one another till complex new ones are formed, and they make others like themselves, and a new dance starts, growing in size and complexity. Living things, masses of atoms, DNA, protein, dancing, a pattern even more intricate. And then, out of the cradle, onto the dry land, here it is, standing, atoms with a consciousness, matter with curiosity. Stands at the sea, wonders at wondering, I, a universe of atoms, an atom in the universe. And this is the last line that I think is amazing. So, we are just a universe of atoms, we are atoms in the universe, but let's never stop looking for beauty and wonder. Thank you very much. So do you have any questions? Do you have any comments? Do you have any?
Excuse me, but in which branch of physics were those laws that were understandable for us?
In which branch of physics were, I'm sorry, what?
That those laws
Roles?
found by computers. You mentioned about some laws of physics.
Ah, the laws of physics. Yes, in Bose-Einstein condensation. In Bose-Einstein condensation. Yes. Bose-Einstein condensation is another incredible thing. You know, they take these very cold atoms, like sodium atoms, and they put them together, and they bring them down to a very, very low temperature, and all of a sudden, these atoms, 30, 100, 200 atoms, become one single object. It's a quantum mechanical object called the Bose-Einstein condensate. Einstein always comes up. And it's so big that sometimes you can see it with your own eyes. But the amazing thing is that this thing that you can see with your own eyes is actually a quantum mechanical object. It's not a classical object. And there they can do things like quantum computing and things like that. And that's what Bill Phillips is doing. Any other questions?
What is the theater in physics?
What is or where?
Where?
Where? Anywhere. I mean, where is? Oh, it's a good question. What do you mean? Can you explain to me what do you mean?
The theater like a performance.
Yes. Well, with my theater company, we do performances in any possible venue. So in the theaters, inside places like this, inside classrooms, big auditoriums, anywhere.
In physics, like in the science, where do you find the theater in the science?
Oh, okay. That's what I thought you would ask, but I didn't understand. What do you find theater? Well, it depends how you define theater. What do you mean by theater? I mean, if theater is having a nice story, like a dramaturgy to tell, then science has a nice story. You know, it has an objective, it has an obstacle, it has characters, it has dialogues, you know, philosophy, it has playwrights. So science has got a lot of theater in it. It has drama. You know Boltzmann, have you heard of Boltzmann? He's the discoverer of, he was the one who developed statistical mechanics. And Boltzmann, in the late 19th century, Boltzmann was, nobody believed him. He was one of the biggest geniuses, and yet nobody believed him when he would say that, you know, we can describe a lot of particles through statistics. Now it's an obvious thing, but at the time nobody believed him. So he got so depressed that he killed himself. And he killed himself just a few days before the Nobel Prize, the people from the Nobel Prize decided to award him with the Nobel Prize. So that's theater.
Drama.
It's drama. Yeah. Marie Curie. I don't know. There is a lot. Any other questions? Yes.
May I ask a personal question?
Yes.
Now, when was the first time, if you remember it, I'm sure you do, when you fall into the state of awe in this connection, when you saw that connection between art and science and this awe?
Well, it's complicated because I've been trying to look for this wonder for my whole life. I remember when I was a student at the university, I was a student of physics and I was also a student of theater. And I had a very good professor of theater that was telling me all the time, you should write about science. And I didn't understand at the time what it meant. I think the real reason why I ended up doing this is because I started reading Richard Feynman. Yes. And the guy I mentioned to you before, you know, remember this thing? Richard Feynman. Because he embodies the sense of wonder. Mm-hmm. And so I was very young, I was, you know, just coming out of high school, and I started reading Richard Feynman, and I realized it's amazing and I want to follow his steps. Of course, Richard Feynman was a genius, so not to follow his steps is really difficult. But nevertheless, you can enjoy yourself. If you don't aim too high and you just go and enjoy yourself, it's great. Any other questions?
Maybe some last question if you have, and then give some time to Andrea to relax, because at 5 there's also a workshop.
Yes. We're doing a workshop here from 5 to 9 today, and again tomorrow from 5 to 9 if you're interested, on science communication, but mostly on using storytelling techniques to develop a way to connect with an audience when you're speaking in public. So it's open to people who like to speak in public, like teachers, researchers that have to talk about their research, professors, anybody here. So you're welcome to join if you want. Well, thank you again for inviting me here. I hope you enjoyed it.